Yes, good evening to all the participants. So, welcome to the day 7 session on energy minimization and molecular dynamics simulation. Before stepping on to today's session topics in this internship and certificate course in AI and ML approaches of drug and vaccine design, can we recap the last session topics? So, what are the last session topics we have discussed? So, do you get some information from this? What exactly did we discuss in the last session? Yeah, we have discussed on virtual screening. Very good. And then what exactly did we discuss? Like virtual screening, we have discussed something called HTS, is molecular talking in drug design. Like actually, virtual screening we have discussed with respect to the talking studies. So one is virtual screening based talking. The other is the high throughput screening analysis. The next is the fragment based screening, also called as lead hopping. So we have discussed this with a few examples. And then we have gone to Autodoc analysis. Yes, first we discussed the how to analyze the results. So the docking results can be shown initially in the form of a 2D structure, that is a 2D interaction. And then I have showed you something using Discovery Studio Visualizer, and I showed you even the atomic context. So with the journal examples I shown, I believe. So I have taken you to two journals and I have shown the talking results. Okay, so the most important results are hydrogen bond interactions, including the bond length, etc. Okay, from the hydrogen bond monitor. Then I have showed you the 3D interaction images. Okay, so these are the outputs I have shown. Along with this, binding energy, whatever we obtained in Autodoc and the KI. So these are also the outputs to be shown after the docking. That's what we have came through talking analysis. Then we have gone through these three types of virtual screening. And we also seen majorly we classify it as ligand based virtual screening can be classified as ligand based approach and structure based approach. And the last one is the hybrid based approach. Did you remember this? So these are the three approaches of virtual screening. So after this, we have gone to hands-on session with the Autodoc PYRX. Okay. So yes, you're right. So now whatever we have discussed on Autodoc and Autodoc analysis, now we can see some new topic related to energy minimization and molecular dynamics simulation. So in molecular dynamics, we discuss in this about molecular dynamics, quantum mechanics, force fields, that is types of force fields, types of energy minimization, Probis charming. So it's a tool for energy minimization and MD simulation using the Chromax. So how the protocol in Chromax can be carried out and how to work with this simulation analysis. Okay, this will be discussing it on today. Now first about the molecular mechanics. Molecular mechanics uses classical mechanics to model molecular models. You know, whatever we study on today is something related to physical chemistry. So one should have a knowledge on physics as well as chemistry. If you see about the molecules has motion. It can be a ligand molecules or it can be a protein molecules. So whatever drug we take, the ligand is going to, if we take in the oral route, it is travel through the buccal cavity and then it slowly moves to the esophagus, stomach, etc. Isn't it? So the drug is moving, and obviously the molecules in the drug is going to have a flexible and movement inside. Similarly, The receptors, whatever receptors present on the surface of the protein, also have a dynamic motion. Okay, so that's what we study in the form of molecular mechanics. Molecular mechanics can be classified into two types. One is molecular statics, the other is molecular dynamics. So generally, the molecule is not present in static position, isn't it? It can be a ligand or receptor. So generally, we observe the molecular dynamics as the default thing in molecular mechanics. And what is a molecule? How a molecule distinguishes with an atom? Can someone tell me what is the difference between a molecule and an atom? So from beginning, we are discussing on different molecules, biomolecules from first unit. So what is the difference between molecule and atom? A group of atoms can comprise a molecule, isn't it? So molecule is a combination of atoms. And if you see this kind of an atom, this we follow the Von Oppenheimer approximation. Okay, so this kind of an assumption we make, and in this any of the tools, if you use Discovery Studio Visualizer, Autodoc, or Python Molecular Viewer, Tasmol, Swiss PDB Viewer, whatever I mentioned are different visualizers for protein structures as well as for the chemical compounds. So in all the visualizers, even the docking softwares, we can assume that one atom is one particle. One atom is one particle. This is how we assume, and even uh, the developers have developed the visualizers like that. Okay, and if you see, this molecular mechanics can be used to study molecule systems ranging in size from the complexity. Okay, now let me take you to the atomistic molecular mechanic fields. As I mentioned, each atom is simulated as one particle. So this is the basic simulation. This is the basis we take in any tool, and each particle is assigned a radius, typically the van der Waals radius. And of course, the particle has the polarizability. Based on polarizability, one can distinguish whether even it is a hydrophilic or hydrophobic nature, and a constant net charge. Of course, this is important related to ionic attractions. So positive charge cation attracts with the anion, isn't it? If you have a cation in the ligand and anion in the protein receptor, then obviously this can have a good interactions. So that's what we call it as an ionic interactions. And so whatever we take a particle has all these kind of a properties. And of course, we also use it in quantum calculations. Bonded interactions are treated as springs with an equilibrium distance equal to the experimental or calculated bond length. Okay, so it can be a ligand or an amino acid of a protein. So generally, we find like this. So the participants can follow that, accept the invitation, Prakati. So even I don't find anyone who can accept you in between. Okay, now let me go ahead with this continuation. So, whatever we are studying is something related to physical chemistry. And one thing we have to remember that in molecular mechanics, we have three types of mechanics. One is classical mechanics, and the other is the statistical mechanics, and the third one is the quantum mechanics. So these are the three types of molecular mechanics: the classical, statistical, quantum. We discuss in subsequent slides about these three types of mechanics. So here in this slide, you can see the types of bonded interactions. So whatever you see here, this is a bond stretch, and whatever we see an increase in angle is the bond bend, and this is rotate along bond. So this the energy of bond stretch, the summation of energy of bond stretch and the energy of bond bend and energy of rotate along bond is the total bonded energy. This is used for talking, this is used for simulation, this is also used for molecular modeling. So this is molecular mechanics is a general concept applicable in all the areas of drug design. And similarly, the non-bonded interactions, the energy, the van der Waals energy, and the summation of electrostatic energy is what non-bonded energy. And of course, the formulas are mentioned here. And one more thing, like the summation of bonded energy and the summation of non-bonded energy is what we calculate as total energy. So this is how finally we calculate the total energy. Whatever we calculate energy for a protein, that won't be a stable. We have to go with a protocol called energy minimization. If and if we go with an energy minimization protocol, then obviously our protein can also be in more folded state. That is, you see protein can be in folded state or unfolded state. The folded state is stable, isn't it? To make a folded state that is more stable, we can go with energy minimization protocol. So whatever energy we calculate in total, that will be reduced after the energy minimization. Now related to molecular modeling tools for building 3D structures, I think we are discussed. If not discussed, we can discuss now. So the proteins can be modeled through any of the uh, techniques like homology modeling, threading, and ab initio. This we already discussed in the previous sessions. And the popular tool what we use for the Swiss modeler and iTaser in online. And similarly, if you want to model the peptides, we can use Discovery Studio Visualizer. If you have the visualizer, you can develop the molecules from there itself. 3D structure of peptides can be developed, or else go with the Vika, okay, and Pepful. And chemical compounds, ACD ChemSketch, ODRG, bond inspiration, RNA, SIM-RNA server. Molecular dynamics is a computer simulation method for analyzing the physical movements. I told you already, molecular mechanics, defaultly we observe the molecular dynamics, and where you can find the physical movement of atoms and molecules, and that too we can find in the form of spring-like motion. An atom is attached to an equilibrium, the atom can move in the form of a spring-like motion. And if we see this Monte Carlo versus molecular dynamics, so in this you can able to see a protein structure. So whatever the blue dots we can see are the amino acids of the protein. If you see some 110 amino acid protein, and if you that 110 amino acid, whatever you can see in the terminal, this can be close to a fifth amino acid or sixth amino acid. So how the distinguished amino acids sequences are close? Just because it is following a folding pattern. Okay, it's like a fold based on the folding pattern. Even the distant amino acid in the sequence can also be present in the closely related sequence, the nearest sequence. Now let me go ahead with the main areas of AMD simulations in drug design. So we can find conformational sampling, energetics, and kinetics. Okay, what is conformational sampling? Here we can go with binding pocket detection and analysis of binding paths. We can also go for rearrangement process. So whatever we do is something related to conformational sampling of MD simulation. So in binding pocket detection, one can know that it will be determining either hydrophilic binding site or hydrophobic binding site. Okay, this is what we have already discussed. Hydrophilic and hydrophobic. That is hydrophobic, it is lipophilic. So, whatever we identify the binding sites is, of course, a form of a conformational sampling of MD simulation and analysis of binding paths. So, if you want to check through conformational sampling, we have discussed three theories of molecular docking: lock and key, induced fit, and conformational ensemble. You remember? So, in conformational ensemble, we will be seeing a ligand, one ligand and one receptor. If you see the different, you can able to see different binding patterns. One ligand is going to dock nearly 10 different poses in the receptor. So whatever we calculate and whatever we analyze, whether that is specific binding site or not, which is going to give a biological effect. So all these things is also a form of a conformational sampling, which comes under conformational ensemble. Of course, which is most binded that we can determine through binding energy. And rearrangement process, detection of structural changes associated with induced bit or shifts in the relative populations of conformations by ligand binding. And energetics, so the simulation of binding and unbinding, that is using the give free energy, we can calculate the energy of binding of ligand with the receptor. So that is actually calculated as change in enthalpy to the difference of the product of temperature and the change in entropy, isn't it? So this kind of a simulation of binding and unbinding. So here I have binding and unbinding is also available. So through that we can able to calculate the how much drug is taken, how much drug is going to excrete. So in pharmacokinetic properties, in ADME properties, there is one property called excretion. So this can lead you to calculate the skin permeation value. Okay, and free energy calculations, absolute or relative ligand binding affinity, and sample of something related to kinetics. So this is something related to thermodynamics, and this is something related to kinetics. That is, in the kinetics, we can able to determine the kinetic properties, whether our ligand, yeah, binding with the receptor, is following a first order reaction or second order reaction. The four orders of reaction, isn't it? Zero, one, two, three. So what kind of order of reaction is followed? That is, whatever ligand receptor complex is formed, so what reaction is followed, this can be determined through this. Okay, so of course all these three can be determined through AMD simulations, and here you find in applications of drug design. So quantum mechanics. So from beginning I was mentioning you, there are three types of mechanics: classical, statistical, and quantum. What is classical mechanics? Classical mechanics basically we study Newton's law of motion. We know that Newton's law of motion, F equals mass into acceleration. So whatever we calculate F equals ma, and the other laws of motion uh, from Newton. So if we follow this, we call this as defaultly classical mechanics. If this is classical mechanics, if you take a protein, can be a small protein of 110 amino acid, for example 110 amino acid. So then for each and every amino acid, we have some 8 to 12 atoms. Whatever we have 8 to 12 atoms. Okay, so if you have 10 atoms uh, in average, 10 into 110, it comes around 1100. That much atoms are there. For each and every atom, there is a motion. We can able to calculate the energy. Whatever we calculate energy is in the form of energy trajectories. So in statistical mechanics, we bother on each and every atom energy. So if I take 110 amino acid and we approximately have 1100 atoms, and each atom has an energy trajectory. Okay, and if you take all this energy trajectory, we go with the statistics. If we deploy statistics and if we try to go for the calculation, we call that as statistical mechanics. So this is used in sequence. After knowing this classical, we try to use the statistical. The third is the quantum mechanics. What do you mean by quantum mechanics? So if you see practically, that is doing wet lab experiments with proteins, DNA, RNA, what exactly we do in spectrophotometer, calorimeter, nephlometer, there are so many kind of measuring instruments, isn't it? Measuring equipments are there. So if you see any of these equipments, okay, including fluorescent activated cell sorter, okay, so whatever equipments we use the light, can be a monochromatic if it is a laser, if we require a laser, or we use a monochromatic light, okay, sodium light, whatever light we use, okay, it is going to hit the protein molecule. If you take a spectrophotometer, take an example like a spectrophotometer. So whatever sample we fed in the cuvette, so we after placing this, we if we switch on, the light is going to pass in the protein. So what is going to happen there? The photons generated from the light, is going to hit the electrons present in the valence shell of the proteins. Then what is going to happen? Excitation happens. So because of excitation, there you can find the movement of molecules. So because of movement of molecules and based on how many molecules are present in the sample, we can measure the absorbance. And obviously from the absorbance, the weight is measured. So what is the physics lying behind? The major physics lying behind in the spectrophotometer, calorimeter, nephelometer, whatever we use is the quantum mechanics. So in that, so however I mentioned, we follow this Croyd-Inter wave equation. The atom, if the photon hits a electron, the excitation happens in the atom. So all these things, if it follows, the atom follows a movement like a wave particle duality. Okay, it's a Schrodinger wave equation. And of course, the particle has the energy, momentum, angular momentum, etc. So, okay, and if you go ahead with an example, quantum mechanics. So, this is what energy trajectory is for one atom, only one atom in an amino acid. I told you average of 10 atoms will be there, isn't it? So, if you see one atom, if you use a slight pulling force, okay, it moves very slowly. But if you give a good kind of a pulling force, how this good kind of pulling force you can get? If a photon it can hit an electron, so based on how much, what kind of wavelength we use, so we can able to find that atoms follow this kind of a sine, cos, or this wave patterns. So through these wave patterns, one can able to determine the energy and other parameter values. Okay, so this is what we call it as quantum mechanics. So obviously, one should remember that the atom is attached to an equilibrium in both the cases, but based on the excitation, you can find the wave patterns. And force field. What is force field? Till now we discussed what is molecular mechanics, quantum mechanics. Now we'll be discussing on force field. So whatever forces we have seen in the each and every atom trajectory, okay, we calculate all the forces of all the atoms to calculate a total force. So and this total force, whatever we calculate, for this we have different force fields. Number one is the classical, number two polarizable, third reactive, fourth coarse grained, fifth we can use the machine learning techniques for determining the force fields, and sixth is even water molecules can be used, modified amino acids, and eighth is other. More about the description of these force fields we see in the subsequent slides. Classical force field. The name itself implies classical. So we are going to use F equals Newton's law of motion. Force is nothing but mass into acceleration. If you want to calculate energy, how to calculate from the force? If you can able to calculate the force, the next step is obviously to go with the energy minimization. Then one should calculate the energy for minimizing the energy. How to calculate energy? The basic formula from the force is force into distance. What is the distance of atom? Okay, so energy is calculated as a force into distance. This is the basic formula we use. Okay, now let me describe on the classical force field. If you use a classical mechanics, okay, then we can use the classical force field. So here, whatever example shown, number one is amber, denotes assisted model building and energy refinement. This is widely used for proteins and DNA. And consistent force field. This is used for polymers metals. Okay, organic chemistry people, polymer engineering chemistry people can also use this kind of force fields for their molecules. Charm. This is a popular force field present in many of the freeware and commercial tools for energy minimization. Of course, this can also use initially to calculate the forces. So the charm, it means that chemist at Harvard molecular mechanics. This is used for both small molecules and macromolecules. So because it's going to have a wide applications in many of the tools, you can see this thing. Charm. Consistent valence force field. Chromos, Chronogen molecular simulation, interface force field, Merck molecular force field. optimize potential for liquid simulations. For liquid molecules, we can go with OPLS. So these are the examples for the first classical force field. The second force field, what we discuss is the polarizable force field. The name itself implies polar groups are important. If our ligand is going to have a polar groups, OH groups, obviously it is we prefer to use this kind of force fields. The first we discuss is the amber. Okay, so amber we already seen in the previous classical, isn't it? This also can use it for polarizable force field. And the next is the amoeba, atomic multipole optimized energetics for biomolecular simulations. Charm and polarizable force field. This is an exclusive force field for this. And similarly, SP basis chemical potential, phased and orient. The third force field, what we see is the reactive force field. The name itself implies if our ligand is going to interact with the receptor, which is going to give a reaction, then we can use the reactive force field. The example is the substrate, if it interacts with the enzyme, obviously this is also a reversible reaction which can form the enzyme substrate complex, isn't it? So what has happened? A reaction has happened, and even here, after one more reaction is going to happen, that is an irreversible reaction. So whatever you see, the enzyme substrate intermediate complex, which is stable or which is unstable, stable for a few seconds only, or unstable, we can call it as this complex is unstable, going to release enzyme and product. So this kind of a reaction is happening with the enzyme and substrate examples, isn't it? So that kind of a reactions we can go with the empirical valence field, and the next is the reactive force field. So this can also be used for uh, calculation of energy. The next, the fourth one, what we discuss is the coarse grained force field. For this, the name itself implies coarse grain. If our ligand is present in the form of grains, we have different drug formulations like tablets, capsules. So how we can find the API in the capsules? So why we take the capsules instead of tablets? Because capsules we have to additionally need gelatin, hard gelatin or soft gelatin. That is extra cost. So what is the purpose to you go with the capsules? If our drug is in the form of a granules and we can't able to compress it in the form of a fine powder tablets, better we can make it in the form of we can fill the granules in the capsules, isn't it? So hard gelatin capsules usually have the coarse grains. So if you have that kind of nature of the drug, then obviously whatever ligand we take, okay, we go with this coarse grain force fields. Number one is dissipative particle dynamics force field, Martini, Sierra, PAM, that is virtual atom molecular mechanics. So these are the force fields used for coarse grains. Now let me take you to the energy minimization. Till now, whatever we discussed is about molecular mechanics, quantum mechanics, and now we have discussed force field and the types of force field. Now we'll be coming to a new chapter called energy minimization. What is energy minimization? So energy minimization, also called as energy optimization, and this is a geometry minimization or geometry optimization. It is a process of finding an arrangement in space of a collection of atoms where, according to some computational model of chemical bonding, the net atomic interatomic force on each atom is acceptably close to zero. Okay, so we try to make a protein more stable by performing this energy minimization. You remember in the previous session, I provided you demo on Autodoc PYRX. In Autodoc PYRX, I, after converting the protein structures in the form of PDBQT, I have gone to the ligand and I also converted the ligands as PDBQT, and I have gone with the energy minimization protocol. So I have done the energy minimization for all the 10 ligands, whatever I docked with a protease protein on yesterday, isn't it? So to make the ligand more stable, okay, we go with this kind of a process. And then if you see the energy minimization, majorly it is classified as steepest descent and the conjugate gradient. So steepest descent, also known as gradient descent, it is the first order optimization algorithm used to find the local minimum or a maximum of a function by taking steps proportional to the negative or positive of the gradient respectively. If this is the steepest descent, the next is conjugate gradient. This is second method of energy minimization. Here, this is an algorithm for the numerical solution of particular systems of linear equations, namely those whose matrix is semi-definite. Yeah, any doubts? Okay, so these are two types of energy minimization. And this actually I skipped when I explained about force fields. So just we discussed about four force fields, isn't it? So one such is the machine learning I told you. In machine learning, we have examples like ANI, which is a transferable neural network potential, and F flux. This is also we can use a machine learning to calculate the electrostatic exchange and electron correlation, etc. Tensor mode, a cloud computing kind of a machine learning technique, we can use it for energy minimization of many molecules. If we try with many molecules, we can go with these kind of tools, whatever mentioned. These are force fields, SCH net, PHS net. So using the machine learning techniques, we have majorly developed these kind of models. Now let me take you to the example for energy minimization. How to do this energy minimization? I told you we already done with Autodoc PVRX, but if you want to do exclusively, we also have one more tool called Probis Charming. So if you see the name itself, Charm, we are using, of course, uh, chemistry at Harvard molecular mechanics. You remember? So whatever we discussed earlier, which comes under classical and polarizable force field. So that kind of a mechanism is used in this online tool to do the energy minimization. Okay, so for this we can go to this URL, and of course for working with charm we can go with this. Okay, so now let me go ahead with the Probis Charming, how it looks like. If you go to that URL of Probis Charming, we get this kind of a window. Either we have to input the PDB ID or upload the PDB file, but it is a must to produce the ID. Even if you have only one chain, we have to give the chain number. If you have two chains and if you want to do with both the chains, give the chain numbers like A comma B if A and B are the two chains. And you can give an better given email it is an optional because it takes some time to generate the result. So for a protein structure, whatever I uploaded, the protein structure I've uploaded is 4W05. So one protein structure I just downloaded from the PDP website and I have uploaded it. And after uploading it, I got numerous chemical compounds which is binding in the binding sites. First of all, for the protein, it first determines the binding sites. The first process what it do is finding the binding sites. For this protein, I think nearly 7 to 8, binding sites are there. That is binding site regions. Whatever I'm telling, binding site is not just binding site. These are binding site regions. Okay. So see this binding site 1, here binding site 2, binding site 3. So whatever a particular region you find here, this might be a binding site 1. And here, whatever you find here, this is binding site 2. Okay, like this, we have different binding sites in the protein. Okay, for each and every binding site, which ligand can bind perfectly from the database of compounds present. So if you see here, this compound is binding effectively in the binding site 1 with more confidence score. Next to that is this ligand 2. This ligand 2, whatever mentioned, is binding with this specific thing. So like this, so based on this, so if you scroll down, you can see the score will be reduced. More the confidence, the more is the binding. So almost these they can show 4.47 confidence score, but if you scroll down, you'll be getting less than the score whatever you got. Okay, so like this, we can find for the different binding sites. This is what probe charm. As I mentioned you earlier, what is molecular dynamic simulation? So here we work with all the types of mechanics, classical to the statistical to the quantum mechanics. So generally, if you see only this quantum mechanics, okay, we take a macromolecules at macroscopic level. So we take a protein in the cuvette, subject to the spectrophotometer, measure the absorbance. So obviously, we take a macroscopic level. We take the entire protein. But generally, how we do the atomic level kind of an assessment, we do with the classical mechanics. We generally take an atom and we calculate the force, etc. Isn't it? So whatever we do in molecular dynamic simulation, okay, whatever we do in the macroscopic level, we analyze up to the microscopic level. That's what we can able to see in this time. Now let me take you to the MD simulation. So if you see the MD simulation, these are the tools: Abalone, Amber, Charm. Already we have seen Charm in energy minimization, isn't it? So we also have a separate, this is of course a part of a simulation tool, and a part of a simulation tool, whatever we see, we can also see in Desmod as well as in Chromax. In Chromax also we have a part of a simulation we have to work with Charm. Okay, and Chromos, the package, if you see Chromax is a package, we call that as Groningen mission for chemical simulations, and many try to use this NAMD. So at present the Indians use Chromax, NAMD, Desmod, and myself I also tried with yeah, Desmod is what a Scroidinger, from Scroidinger package. Okay, so we have also tried with the Scroidinger package this, and NAMD is actually nanoscale molecular dynamics. The advantage of Chromax is this is a freeware, but one major problem with these tools, if you want to install this Chromax freeware, this is a commercial one. Of course, Desmond is also commercial, so we have to pay for it. Okay, so if you want to try, the best thing you can try is the Chromax, but still we have some disadvantage here. Whatever Chromax we have to work, we can work only in the Linux operating system. So at present, for the past 5 years, even in the Windows, they brought a kind of a Linux interface, and in the Windows we can type the Linux commands through that interface software, and we can work the simulation. Okay, so one is we should have a knowledge on Linux commands. The second thing is we should have a dedicated workstation. We can't even able to work with i9 laptops. The laptops are not used for simulation. The laptops can be used for simulation analysis. For example, after talking, the next session on the next day I've taken you on talking analysis, isn't it? Like this, after doing simulation, if you want to go with an analysis, we can use laptops. So one should have a workstation to work with this Chromax. Anyhow, I will be giving some information on this Chromax, how to work, etc. And the eighth is the Q and ninth is the answer. So Chromax is the freeware. The remaining role we have to pay something. And Chromax. Uh, so if you see in Discovery Studio, in Discovery Studio also we have simulation that we can able to work in Windows itself. But it's a commercial one, isn't it? Okay, if you want to go to this chromax.org, we'll be getting this kind of a homepage where we can use the download option to download the software. What is a Chromax? It is a versatile package to perform molecular dynamics. Okay, and if you see the Chromax, we have so many tools present in it, uh, present for MD simulation. For example, I told you if you want to work with Chromax, we should have a knowledge on Linux commands. So using the Linux commands, one can able to use these tools. And what are these tools actually? These 12 tools, if you see, the first tool is GMX setup. This produces a topology using Chromax for a given structure. Topology, the parameters to be used. For example, even if you see the Autodoc, if you are doing the molecular docking using Autodoc, initially we have downloaded the protein and ligand as PDB files. Later, we have included the hydrogens. Then we have included the ions, and then we have gone with the hydrogen ions and not converting the file as PDB-QT format. So we are doing all this kind of process, isn't it? So in topology, we are altering some parameters in this complex file. Generally, what is the major input you take in MD simulation? In MD simulation, we take the ligand receptor complex. If you want to analyze the binding of ligand receptor, we take the ligand receptor bounded complex. That is final thing. After docking, we got something like guaranine protease. That's what we have talked, isn't it? Guaranine protease complex. So that complex you have to take it as an input here. That is output of docking is an input of empty simulation. So if you want to work, we have to work with the Linux commands, and these commands, the second command, gmx solvate, is to solvate a system. Defaultly, we use water as a solvent for estimation of binding size in docking as well as an empty simulation. So if you are using a gaseous molecule kind of a simulation, then air is the uh, air is used as a control system. Okay, so we first solve a system using GROMAX and GMX-EM for energy minimization, and GMX-SIM for MD simulation using GROMAX. GMX restraints, calculate position restraints. And whatever I have shown, these kind of commands, etc. And if you want to work with GROMAX and if you want to get expertise, so all these things is a form of a PhD research. Only the PhD research students, if they want to complete PhD in computational part alone, they work on this kind of a simulation calculations. They try with the proteins of different isoforms, and they produce in the form of a PhD thesis. So just practicing with the demo is easier, but if you practically, if you're trying with your kind of a proteins, you need much more time. And for training in this GROMAX, I know few colleges, they can give 15 days exclusive training for in simulation alone. Okay, they provide MD simulation training for 15 days. That to 15 days, you have to stay in that college. You have to stay in the campus, and you have to learn for 7 to 8 hours. So nearly 7 into 15. This much hours you have to train. Okay, so there is a lot to know about in the simulation using GROMAX. I'm just giving you some kind of a description before learning all this. And if you want to implement in your PhD research, instead of simply you are not touching the in vitro or in vivo experiments, still using computational, you can complete PhD. But we need more knowledge on these computational skills. To work with the GROMAX, one should also have a knowledge on Python programming, and one should also have some knowledge on Perl programming. Okay, so Python. So who knows all this? Only those who are working in computational biology field. Okay, the remaining thing, whatever I'm taking you from the beginning, anyone can able to practice. But for this, one should have a workstation, and one should work with the Linux operating systems. Okay, one should have a knowledge on Linux commands. So to create an index file, GMX maker NDX to extract energy components, GMX energy, GMX trajectory, GMX edit conf. So like this, you can see the number of programs. First, we can see an analysis thing. So the first major MD simulation analysis is RMSD. RMSD stands for root mean square deviation. You remember this RMSD we have also seen in where exactly we have seen RMSD in the earlier session. Can I ask you the question? So we have discussed RMSD in somewhere. Where exactly we have found RMSD? So now I am showing you in simulation. But this is looks like a repetitive one. But still we have a slight change. If only if you remember where exactly I have taken you in RMSD, then I can tell you what is RMSD in EMD simulation. how it is. How to assess the quality of a protein? So this is my next question, which can give you a hint. How to assess the quality of a modeled protein? So modeled protein, I mean modeled using computational techniques. What are the different methods to assess the quality of a computationally predicted protein structure? Yeah, participants, kindly come with your answers. So very simple, isn't it? Well, we have MCQ also the last day. Somehow ChatGPT can help you, but still we have to keep it in our mind, isn't it? These are some basic things we should not forget. How to assess? See, I told you who is the father of bioinformatics in India. You remember father of bioinformatics in India? But try. But homology modeling is just for predicting the 3D structure of protein. Yes, good. Ramachandran plot. Good. When I told about father, he immediately got with the scientist name. Ramachandran plot. This is number one. And number two, I told you to use RMSD, isn't it? Whatever we calculate root mean square deviation, we, where exactly we find this RMSD here, comparative modeling. So whatever computationally structure we have predicted from homology modeling, threading, or ab initio, we have to compare with X-rays, I mean, gold standard technique determined proteins, X-ray crystallography structure, or NMR structure, cryo-electron microscopy structure. If and if you compare this computational structure versus wet lab prediction structures, then only we can come to know how exactly and what precision the protein structure is predicted. So if you find the difference between the atoms is more, then the quality is poor. If the distance between the atoms is less, then obviously the quality of protein is good. Okay, this is how we can assess. Here, in MD simulation in RMSD, we determine whether the ligand is bound with the receptor or not. If it is perfectly bounded, if the ligand is having a more stable binding with the receptor, we can able to assess using this RMSD. That we are just using in comparative modeling of proteins. Here, we are assessing the quality, I mean, assessing the stability of ligand binding with the protein. And to work with the RMST, we use the GMX command. GMX is Chromax. Then we use the RMS. GMX spacebar RMS. And then we use a parameter. Then we use this intermediate file, XTC protein. And then we give a, and finally, whatever we give this RMST.xvg, this is the output file. So the output file, whatever I shown in the form of a graph is this. And if you want to open this XPG, obviously we need one tool called XMCraze. Other than Chromax, we should use a few more tools to work with supporting this Chromax. To finalize the outputs of RMSD, RMSF, we use this XMCraze tool. And to calculate RMSD, this is the formula we use. And how to infer this result, a ligand is bound to the receptor. If you see here, so from here to here, that is stable. Okay, that is, it comes around 30, 30 to 70, 30 to 85. Okay, or 30 to 80. So the protein is stable, okay, from 30 to 80, and the RMSD is 0.75. So actually, the RMSD is mentioned in y-axis and time in nanoseconds is mentioned in x-axis. This protein, whatever we worked, okay, we worked for a simulation time of 200 nanoseconds. And if you want to infer the result, we have to first draw a line, and you can check how stable and on how much time it is stable. So here also you can find the stability. After this, that is after the 85. So 85 to 150, it is more stable. and you can see it comes around zero point 0.8 RMST. So like this, we infer the results. Okay, so a protein over a period of time stability is measured here. Now in the second example, whatever I've already circulated the papers, we remember with A with cardiovascular receptors, Pyrimidine B with hepatocellular carcinoma receptors. Other than talking, I also performed a simulation. So this is something related to the hepatocellular carcinoma receptors, epidermal growth factor receptor and caspase-3. So this is EGFR with ligand is shown in red color. So EGFR with ligand is red color. EGFR without ligand is black color. So just because with ligand is less, the RMST of with ligand is less when compared to the protein alone, we can tell our ligand is binding stably with the receptor. So this is how we can conclude the result. So how to check whether the ligand is binding stable? So just by checking with the ligand receptor complex and checking the receptor alone, checking the receptor alone without binding with ligand. So similarly, tried with the caspase 3. Even in the caspase 3, we got this kind of a result. Okay. And the next thing, next output of simulation is MD simulation using RMSF. Here it is a measure of the deviation of the position of particuli with reference. Actually, one can remember that C alpha fluctuations were determining through RMSF. To work with RMSF, come with the JMX command, RMSF parameter, give the file, and finally you give this RMSF.xpg. So this is the output file we get. Okay. So this is the, if you open the output in the XM trace, we get this kind of an output. Here you can see the RMSF is shown y-axis in angstrom, and in the x-axis it is shown in residues. In RMSD, in x-axis you can find in nanoseconds, but here the protein amino acid residues. If there are 200 amino acid residues, all the 200 amino acid residues fluctuations you can see. So I told you we determine the C alpha fluctuations. The C alpha fluctuation should not be more than 1 angstrom. If it is less than 1 angstrom, the RMSF value is stable. The ligand is binding stably with the receptor. So this is the peak we got. Only one peak we got. So in the residue, nearly 100 to 115. 100 to 115 amino acid, you can able to find the RMSF is around 0.55, something like that. But still, it is less than 1. 0.55 is less than 1 angstrom. So this is stable. Our ligand is binding stably with the protein. So RMSF can also be compared with the ligand and without ligand. That is trying with the ligand receptor and trying with the receptor alone. So if you see the red color is with ligand. So that you should not have any peak above 1. So the red color, this is the maximum thing which is less than 0.5. And also without ligand also we are getting this around 0.5. But it's not crossing 1. So the ligand is binding stable. Here, in this case, caspase 3 with ligand, you can see it's crossing 1. So this is not stable. So whatever we bind our plant compound with the receptor is not stable. So this is how we conclude. And the next output what we show is the radius of gyration in the MD simulation. For this, use gmx gyrate command. And final output what we take is the gyrate.xpg. This is the output of gyrate.xpg. Here you can see the radius of gyration generally measures the moment of inertia. So in atoms, I told you torsion angle, bond bend, bond stretch, rotating along bond. So such a kind, if the atoms, if we see the glycine amino acid, you have three flexible rotations, pi, psi, omega, etc. So where you can find this radius of gyration more, isn't it? So if you see the radius of gyration here also we check as similar to the RMST. So here it is stable. So from where around around 80 amino acid to 125 amino acid, you can see the radius of gyration is stable. And similarly, after that, you can find stable somewhere here. So like this, but mostly it is not stable. The moment of inertia is not stable. But here in this 80 to 125 and 150 to 200, it is stable. And whatever value you get in radius of gyration value, you can show that. Okay. And binding free energy determination. So if you see, if this is your ligand and this is our receptor, okay, if we take the ligand receptor, here in this case receptor alone, and here it is a ligand alone. Okay, so we can, if we need all these three, so that's what we call it as three trajectories. If you use these three trajectories for calculation, for example, del G of binding is calculated as del G of complex. The complex is del L minus del G of receptor minus del G of ligand. Then it is what we calculate as change in give free energy of binding. Okay, the change of Gibbs energy of binding is calculated using this correlation. So where we are using all the three trajectories in consideration. So whatever we use the three trajectories is what? Molecular mechanics, generalized bond surface area. Molecular mechanics, generalized bond surface area. If you require only one, that is ligand receptor complex alone, and if you calculate and if you represent the energy, that we call it as the molecular mechanics Poisson-Boltzmann surface area. But if you need two trajectories, that is one ligand receptor, okay, and the other is the ligand alone. If you take these two alone, that's what we call it as two trajectories. Here we have to use linear interaction energy approach. So the energy can be determined through three different trajectories approaches. One trajectory, three trajectory, and two trajectory approach. And these are some of my results. Where I just try to talk with normal protein with multiple ligands. So for multiple ligands, multiple colors. SASA, solvent accessible surface area analysis. Hydrogen bonds. So we can also get the hydrogen bonds like this. PCA, principal component analysis. When we have to go with principal component analysis, if we find our ligand is showing high RMSF fluctuations, we can go with this RMSF, I mean PCA analysis. Principal component analysis. Okay. So today I have provided you the demo. I have completed the force field energy minimization, etc. And then I have taken you to the MD simulation. Only one tool I just projected to show you, that is Probis. For the Probis, initially it is asking you to upload a file. So I'm going to click a file. So I can take a file, whatever we have used it. So what protein we have worked? Protease.pdb. I just uploaded the protease. I believe in the protease we have A chain. Okay. So this is actually used for energy minimization. So I just open the protease in the notepad. So in the notepad you see actually A chain is available. So I'm going to feed as A chain. Whatever I fed, protein, chain A. And then email ID I have provided submit job. So it's working 0%. It takes some time. So if it takes some time, if we get a result on tomorrow in my email ID, I can open my email ID and can show you the result. So today I have completed this session. So on tomorrow we'll be discussing on genomics and proteomics. Any doubts, you are welcome to ask it. Right. Any doubts? If no doubts, thank you very much for your patience and interaction and joined even during the holiday. Have a great day to you all. Bye.
Thank you, sir.
Thank you.